Hello. Do you hear me?
Yep, I can hear you.
Sorry, for some reason, I'm not sure if I was in the wrong link or something. But, let me check. Oh no, I was in the right link. Did you join very recently?
Oh yeah, just now.
Okay. That's why I got confused. Okay.
Yeah. Oh, it's
Yeah,
right.
yeah, I was looking for a different if I was in the right
There,
link.
yeah.
Okay. Do you see the slides changing?
Yes, I can open both. With you, it's easy.
Okay, awesome.
Yeah, for external speakers, usually they've not used me. They've used what's called Zoom or something like that. So it's they may not have permissions or something, but now it's pretty easy.
Okay, awesome. So this changed and everything, right? Okay.
Yeah, that's all fine. So yeah, what will happen? So I just started the YouTube stream. So some people may join that. Some people may come into the actual talk. The, I've noticed that recordings are far more popular than the initial
Oh,
talks, because of time zones and meetings and whatnot.
yeah.
But
Just one warning. If we can start the meeting 1 or 2 minutes late, just because I need to get my room. That I'll have to.
that sounds, and that's far more common. You always get people to be sometimes you be late.
Okay. Just double checking. The talk is 1 hour, but I'll make it shorter so that we can have questions. Correct.
Perfect. Yeah. And also take notes. So I don't know if you noticed that I published notes alongside. So in fact, a bunch of people who don't really care, but kind of care, look at the notes and move on.
Okay.
So I have found that to be pretty useful because the talk series is so broad. Most people don't care about most things really, but they kind of vaguely catch up and say like, oh, I really want to watch this. And so yeah, sometimes they just do that. But I think by default they do that. Just read the notes.
Okay. I'll go find my room.
Okay, sounds good. Yeah, see you in a second. You'll get a couple more minutes as people are joining in.
Okay, sounds good. Do you hear me well now?
Yeah, now it's good. No more echo. I think we have quorum. So let me start recording. I'll give you a really brief intro and then we can start.
Sure.
So hi everybody. I'd love to introduce Ferran Alet from Google DeepMind, and he's done a lot of work on machine learning, what's called meta learning, and has recently applied his work to weather forecasting. Welcome, Ferran.
Thanks for the introduction. Yeah. So today I'm going to present on behalf of the GraphCast team our work on mid-range weather forecasting. So the paper GraphCast, you can already find it on Archive, and we've also open sourced the code on GitHub. So what's our problem? Our problem is essentially predicting the weather 10 days ahead globally in the entire Earth at 0.25 degree resolution, both in latitude and longitude. So more concretely, think about it as kind of, we have essentially a grid around the Earth, and we have both surface variables as well as atmospheric variables that we want to predict, like temperature or wind speed or geopotential. And each one of them looks like this, like a dynamic field, like the east-west wind in the surface, also surface temperature, and again, other atmospheric variables like temperature at 500 hectopascals. But these are only 3 of the more than 200 variables that we modeled. The intuition and motivation of this work is that traditionally weather models have been essentially using classic physics, so we roughly know the exact laws of physics for the weather. If we had perfect information, of course we don't have perfect information, and both because we have imperfect sensors and as well as because we have finite compute. So weather researchers have had to make lots of approximations on top of this. So our hope is that machine learning can directly learn a better approximation of the weather given these constraints, because we have lots of data. In particular, we found that indeed we are able to learn more accurate as well as much faster models than state-of-the-art NWPs, numerical weather prediction models. And we present GraphCast, which is the best model in mid-range weather prediction. And we also present a careful comparison against the state-of-the-art NWP model, HRIS, from the European Weather Agency. This is particularly tricky to do, given some of the circumstances, which I'll go on in more detail later. And finally, one thing that is not obvious directly is that we obtain better RMSE metrics, like usually we do in machine learning, but we also want to get better consequences for the end user. So we also check that these better predictions in terms of metrics also translate to better prediction for extreme events. So more concretely, the model variables, as I was saying, are different atmospheric variables, so geopotential, specific humidity, temperature, and then wind in the 3 cardinal directions. And we model this at 37 levels of altitude. And in bold, you can see the ones that ECMWF, this European Weather Agency, reports in their scores. We also have surface variables, which are particularly important for humans, like temperature, again, wind, the pressure, and also precipitation. And finally, we also have some inputs that can be directly predicted by hard-coded models, essentially like the time of day, latitude, longitude, time of the year, whether there is land or sea at a specific location, and the altitude, and also how much sun is radiating there. So one thing that is not obvious is that the weather is very, very large for typical machine learning standards. So here you have an image of MNIST, and here you have ImageNet, the classic computer vision benchmark. And our model GraphCast, because it models at 0.25 degree latitude longitude resolution, it's really, you should think about each variable as being a very high resolution image. Not only that, but images typically have 3 channels, RGB. In our case, we have more than 200 variables. So now each time step prediction is going to be much more than a single image. And finally, because we predict 10 days ahead at 6 hours resolution, we actually predict kind of 40 frames, but each frame has 200 variables. So that comes to about 35 gigs, which we believe is probably one of the largest output examples in machine learning. So a question is, why now? Why has this?
First, a question about the data set. So we don't have weather stations stationed that finely in space. So are these reanalyses of fast weather?
Yeah, exactly. This is literally the next bullet. If you're asking about the data set, yeah. So why now? There's three key factors, and the first one is data. So we have available the ERA5 reanalysis, which is provided by the European Weather Agency. And it's worth noting that this is a simulation. So a simulation basically means going from raw weather sensors, right? Like satellites, like globes, things like this, or like ground measurements, to the kind of an estimation of the true weather state. This is still based on classic physics, and this is not based on machine learning. So we take kind of an estimation of this and reanalyzed more than 40 years back. So we have a massive data set. In terms of size, and that's why that's one of the key factors in deep learning typically. And it's also very high quality data because there's been a lot of compute effort gone into amortized into this data set. The second key factor is compute. As you know, it's now more and more useful for getting performance, and in particular we train on 32 TPUs. And this just goes along the line of increasing scale in machine learning models. Our model itself is quite small, but as I was saying, each input-output example is very, very big. So we really need the compute. But note that this compute is different than the typical compute in weather models. So before, weather models were using servers of around 10,000 CPUs. And now we just use a few TPUs in order to train. And at inference time, we only need a single TPU, which for non-Googlers is essentially like a high-end GPU. And we can do in 1 minute what it used to take a server around 1 hour and thousands of CPUs. And this is because, again, we leverage parallel compute. And the third thing is progress in deep learning algorithms. In particular, we build on graph neural networks. So essentially, we are going to build a mesh around the Earth and think about this as a graph. And essentially, the weather is going to inform nearby weather states by passing messages along this graph. So the kind of short story of how graph neural networks work is they have a latent vector on each node in the graph. And they also have a latent vector on each edge in the graph. And nodes inform their neighbors. And so they update their own latent vectors by sending messages to nearby neighbors and then updating themselves based on the received vectors. So why do we build on graph neural networks? They have, in particular, key inductive biases that we'd like from weather. One inductive bias, for instance, is locality, because nodes only send messages to their neighbors. We are essentially encoding the fact that weather is local. And so in a short period, the weather in London is only mostly going to depend on the weather in the UK. It's not going to depend on the weather in Brazil in a short period of time. And the second thing is equivariance. So that means that because we reuse the same parameters, the same neural networks on all the nodes in the graph, we're essentially encoding that the weather function is the same in the UK than it is in Brazil, than it is in Africa. And that allows us to be much more parameter efficient than if we didn't encode this inductive bias. Of course, these three key factors have been playing on the entire community, not just us. So, so there's been progress in weather using CNNs, also graph neural networks, Fourier neural operators, as well as transformers. And it's really been a wave in weather prediction using deep learning to improve upon classic physics. So let's go into more detail on how our GraphCast, our model works. In particular, we receive an input weather state, and we are going to predict the next state, in particular 6 hours from now. So by using GraphCast, which here it's shown as a black box, but it consists of 3 parts. So the first one, the encoder, is essentially going from the grid, which is, as I was saying, you should think about it as kind of an image, so a rectangular image. But this rectangular image is not uniformly distributed around the Earth. It doesn't know about kind of the spherical properties, the spherical geometry of the Earth. So we have to map it up to a mesh. And so this essentially informs locally the nodes on the mesh.
Then we use a processor, which essentially propagates the information around the mesh and informs and predicts a latent vector that informs about the next state of the weather. And finally, we go back to the grid because that's where the predictions are needed. And so we have a decoder that decodes from the mesh back to the grid. This mesh that I was telling you before is actually what we call a multi-mesh. So essentially, we have a few edges that propagate the information very far, and many edges that propagate the information locally. And how this is made is we take an icosahedron and we iteratively divide each triangle into 4 smaller triangles, and we do this up to 6 times. And so we're going to have kind of a few nodes that propagate the information far, and then many edges that propagate the information locally, and we kind of pull all these type of edges together, resulting in more than 40,000 nodes and 300,000 edges. Finally, we have autoregressive training. So the idea is that the weather function now is going to be the same as the weather function in the future. So really, if we want to predict 10 days ahead, we don't use a single neural network call that predicts directly 10 days ahead. What we do is we predict 6 hours at a time, 40 times, and we train for this autoregressive training, so essentially applying the function multiple times to work well. Our training loss is essentially mean squared error, and the average essentially happens over the forecast time, so we have about 40 years of data. We also have to average over lead time, so we train the model to do well both at 6 hours, at 12 hours, and at 18 hours, etc. And we also average it over the entire globe. And again, over variables. We have more than 200 variables, so we also have to average over them. But comparing variables is quite hard, right? You cannot just output this directly because one variable is in Kelvin, another variable is in meters per second, etc. So you have to weight them. And one way we weight them is by using the inverse residual variance. So what this means is essentially that if you were to predict the input if you were to predict the present state for the weather 6 hours from now, on average, you would get a loss of 1 for all the variables in the data set. And that's what we compensate for. Then we compensate for different variable level weights. We give them, different levels in the atmosphere, we give them different weights, because we notice that lower levels in the atmosphere both matter more to humans and are also more impactful of the weather because there is higher wind, higher air density there. And finally, because the grid puts more points near the poles than in the equator, you also have to compensate for this. As I was saying, we have autoregressive training, and most of the time we spend it on training a single step. So in particular, we do 300,000 steps at a single autoregressive step, just training the model to do well at 6-hour prediction. And we do this for multiple reasons. Number one is that it's faster, because if we were to train doing multiple autoregressive steps, that would mean that if we train with 5 autoregressive steps, it's going to take 5 times more. And so we found it useful to just train autoregressive with a single step. And the second one is that if you start with a very bad model and you train it autoregressively from the beginning, this can lead to instabilities. So we wait until we have a very good model before starting to train autoregressively. And this process takes about 3 weeks of training, so it's quite compute intensive. And then we fine-tune up to 3 days. So essentially, we do up to 12 steps, 12 autoregressive steps, because it's 6 hours prediction. And this process takes up to 1 week. So these are the predictions coming out of the training of our model. You can see that they look...
A question on technical approach. Yeah. So well, how did you mesh it? Because you kind of quickly went through it, but it seems like it's an important part of it. You have if you can go back to the picture, it seems like it's a mesh that's different on pole. I mean, it's the mesh cells are smaller on poles than on the equator. So why that choice? Because wouldn't it bias your model compared to like a hex?
Exactly. So that's why we have the mesh. So the grid is given to us by kind of the problem setting. So the weather community, they evaluate in different ways, but the most popular way is evaluating in the grid, this rectangular image that I was showing before, and that has more points nearby the poles. The density near the poles is very high compared to the points in the equator, and that would bias our model. So that's why we create the mesh. And if you look at the mesh is more uniform around the globe, right? And so the mesh doesn't have higher density in some places than others. The mesh, you can find it
that helps a lot.
the bottom row. And so we first move to this kind of more uniform distribution of nodes. We propagate the information there, and then we go back to the grid. And the grid is kind of problem specified. We cannot change it.
Okay, and that's how you're dealing with speed of causality, because for every causal factor, you're going to have different speeds, but you have a mesh for every speed.
Yeah, exactly. So we think that some processes move faster and some processes are smoother than others. And so that's why we have different layers of the mesh. All these edges happen simultaneously. So all the message passings happen simultaneously, both the long edges and the short edges. And the model learns to use all the different edge lengths to propagate different types of information.
Okay, then one more thing. You don't have a notion explicitly here of time or history dependence, but you have longer distances. So it means your maximum distance of history is one, I guess quarter way around the Earth, if I get it correctly. Is that right? And is that good enough?
Yeah, that's a good question. So technically, we have 16 message passing steps. So there is plenty of time to go around the globe multiple times. So the model can learn some non-physically plausible physics. It just learns about kind of data correlation and data information. It's not bottlenecked by kind of speed of sound or things like this. Now that we're on the topic of temporal things, the input of the model is actually not just the present, but the present and 6 hours before. In theory, weather is Markovian, but we found that probably due to partial information and kind of issues with data simulation, it was useful to have 2 time steps so that the model knows a bit about the dynamics of the model of the weather as well.
Okay, and actually, maybe it's a good time to ask this. So it's the whole Earth 40 years, but for the Earth, 40 years is not very much.
Yeah.
So how badly is overfitting hitting you? Because it is just 40 years of a complex system.
Yeah. So that it's interesting because 4 years sounds to some people it may sound initially like a lot, but actually in terms of time steps at 6 hours, there's not that many examples.
Yeah.
But crucially, each example is super rich in information. There's lots and lots of losses. So actually, it's in terms of number of targets. If you think about it per time step, it's not that many. There's not that many time steps. But in terms of actual targets, there is a lot of targets. We found that before doing autoregressive training, so if we were directly predicting, let's say 10 days ahead, there was huge overfitting. Once we moved to autoregressive training, the overfitting diminished a lot. We still have a small L2 penalty, but we don't think we're overfitting too much, to be honest.
All right, thank you.
Yeah, because the data set is actually huge in terms of number of targets.
Right.
Yeah, it's a good question. Okay. So, as I was saying, we have this forecast, which again is the median error in 2018, which was our test year. And you can see that the predictions of GraphCast in the bottom look reasonable compared to the ones from HRES. And you can see the errors also, of course, increase with time. And hopefully you can see that the errors in HRES on the top are slightly higher than those of GraphCast. This is hard to see in images, so let's look at it quantitatively. Here we have a very standard metric in the weather community, which is geopotential 500. 1 second. And then we have RMSE, so a measure of the error in terms of time. And of course, we're going to do worse as the lead time goes on, right? And lower is better. And you can see that GraphCast in blue is significantly better than HRES in black. For now, disregard the dashed line. I'm going to talk about it later. And this, of course, to kind of remove this time dependency, we normalize by HRES, and we essentially look at the percentage of improvement of GraphCast on top of HRES. And you can see that, for instance, for Z500 is about 10% improvement. So we have 10% lower RMSE. And this can be done for many variables like 2-meter temperature or surface wind or specific humidity at 700 hectopascals. And for each of them, we're going to have a percentage of improvement depending on the lead time. So for instance, you can see that at 2T, at the very beginning, we are slightly worse, and then we become about 10% better, and then towards the end, we become just slightly better. And for other variables like the surface wind, we can be up to 30% better at the very beginning. But as I was saying, there's many variables. So we have to find a better way of representing all this information. And we take the ECMWF scorecard, which is essentially just a color map of these residual, relative scores. In blue, you can see where GraphCast is better, and the deeper the blue, the better GraphCast does, and the opposite, the deeper the red, the better it does. And you can see that essentially we also have lead time going towards the right, and we have all the different altitude levels for geopotential. And then here we have all the different variables and lead times leading to more than 1,000 different targets. And the summary is that essentially GraphCast does better on 90% of those targets. And you can see that especially on the lower levels where humans care more about this, well, GraphCast does particularly better. So of course, it's great to see that GraphCast can do a great job on these kind of RMSE metrics. However, the real world uses weather models that go far beyond these RMSE metrics. So we thought it would be interesting to study some of these extreme weather phenomena that heavily impacts people's lives. We decided to focus on 3 applications, tropical cyclones, atmospheric rivers, and extreme heat, to show how GraphCast performance translates to these settings. We start with tropical cyclones, and we essentially re-implemented the weather agency in the European Weather Agency cyclone tracker and applied it to GraphCast. And we took the cyclones from the Ivy Tracks dataset. And in this plot, you can see Hurricane Maria from 2017, which was one of the first storms to ever hit Puerto Rico and the surrounding areas. And in black, you can see the ground truth for 5 days, and in red, you can see the forecast for ATRIS. And here we observe that the ATRIS track totally misses the true track after a few days, and GraphCast on the right is much closer to the ground truth for the full 5 days. So of course it's that was a single specific date, but measuring across years of hurricane data. Yep.
Can I ask, how do you extract cyclones? This is not really a GraphCast question, but out of interest, how do you extract cyclone trajectories from your stack of 227 variables?
Yeah. So the ACMWF has a open source, no, not open source, the implementation of the tracker, but they describe how the tracker looks like. And so it's essentially a combination of mean sea level pressure and then the winds. So the center of the hurricane is essentially like a local minima of mean sea level pressure. And there's also a few criteria on locally on like the vorticity of that depends on the speed of the different velocities nearby. And there's I forgot exactly, but there's also another criteria on the gradient on the pressure. And so there's a few technical criteria. I can follow up with you if you want on the specific, but think about it as several criteria that the local weather has to satisfy, and then you have essentially a tracker that just propagates and tracks this local minima of mean sea level pressure. To initially detect the cyclone, we start from the Ivy Tracks dataset. So there's nothing in our system that predicts here there's going to be starting a cyclone, but it's very easy. Well, not very easy actually, but it's relatively easy to track the cyclone once we know. Okay, if we're given here is the starting a cyclone, please track it. There is enough information to know where the cyclone is.
So the cyclones, it's a point in space. It's a 2D coordinate, and then it's a function that takes maybe the surface level variables and then spits out maybe the previous location and tells you where it's going to move next, basically.
Yeah, exactly. So you have so here we're talking about the center of the cyclone.
Yeah.
But to really know where the center of the cyclone is, you need to look at a nearby area. Think about it maybe like 3-4 degrees, and then based on the wind, for instance, you know, okay, if there's wind going east, then the cyclone has to move east. And so you estimate, the 6 hours from now, the cyclone is going to be near this area. And then near that area, you start looking for mean sea level pressure local minima. And then there's a very specific algorithm that the CMWF open source and published, sorry. And then we essentially re-implemented that. One thing that we found is that if we literally re-implement their published tracker, it doesn't work quite as well for us because their tracker works for their predictions, and so we had to change some of the constants, some of these magical constants. Like for instance, there is different thresholds on what a cyclone has to satisfy to keep being considered a cyclone, or which points. Not all the local minima of mean sea level pressure are good cyclone-centered candidates and things like this. So we kind of search on validation data for some of these conditions for being a cyclone. Am I answering your question?
There's a historical database, I guess, of previous cyclones.
That's right. So the IBTrACS data set, it's literally a data set of cyclones. So the way this is collected is they have different weather agencies around the world, and then they had all these conjectures about where the cyclone was at each time step. They don't quite agree with each other, and the IBTrACS picked a reasonable agreement between all these different weather agencies to kind of get at the gold standard on where each cyclone was at each point in time. And so we have, I forgot how many years we have, but we have probably more than 20 years of cyclone tracks available, and that's what we use for evaluating the cyclone performance.
I see. Thank you.
And yeah, how this looks like is it's essentially latitude, longitude, but there's also, if you're interested in cyclones in particular, there is a lot more information on that data set. Cool. So
another one. So these 9 hours and 20 kilometers, what do they mean?
Yeah. So okay. So yeah, on the left we see that we see the median track error. We reported median on the main text because we found that a hard-coded tracker sometimes makes mistakes and just mistracks the true track predicted by our model. And so this was less sensitive to these outliers, but we also do better on mean. And what we see is that if you look at HRES and GraphCast, you see that the GraphCast error is lower, right? And what these 9 hours mean is that we can essentially warn with the same level of accuracy as HRES 9 hours before HRES, right? Because our error is the same as HRES 9 hours later. So we can warn with the same level of accuracy with 9 hours more. And on the plot on the right, we essentially look at kind of the vertical distance for a single lead time, how much lower error we get with GraphCast than with HRES. And so we can say the location, the center of the hurricane, we can predict it with 20 kilometers better than HRES. Did I answer your question? Yeah, awesome.
Yeah. Oh, and then one more thing. These are live things. So one challenge for dealing with any weather data is that you have satellite sensors and ocean buoys and whatnot. It takes a while for them to go up to central servers and then go into like a reanalysis like grid, which you typically don't get in live. But your data set obviously is reanalysis. So how did you bridge that gap in freshness of data?
Yeah. That's a great question. So I'm going to talk about this in a lot more detail in a few slides. That's number one. Number two is that even HRES, so in practice, how it happens at deployment time is that you do reanalysis, I think, for like you're constantly getting the sensors, and then you actually do reanalysis and go back 3 hours into the past and then predict from 3 hours into the past. That's how weather prediction is done in practice. So you use the present to inform the model of 3 hours ago, and then you predict from there. There was a bit different, like our data set doesn't quite work with these 3 hours, and so we had to be very careful with that. And I'm going to talk about this later.
Excellent.
Cool. We also looked into atmospheric rivers, which are a weather phenomenon that transport large amounts of weather vapor away from the tropics and can cause heavy rains. This is characterized by the integrated vapor transport, which we call IVT, which is something that can be computed from the weather variables that GraphCast predicts. And we evaluated this over the US West Coast during the cold season, which is a season known for these atmospheric rivers. And we compared the performance against HRES. And we found that GraphCast now it's not 9 hours, it's 1 day of accuracy better in IVT. And note that this IVT, we did not directly predict this. This is a nonlinear transformation of the weather variables that we do predict. Finally, we studied extreme heat. And in this slide, we studied the capability of GraphCast to predict the top 2% surface temperatures using precision recall curves. And we do this as a function of lead times, and that's why you have kind of 3 types of curves plotted in different shades of the color. we find that for long lead times, the GraphCast curve in blue is above the age-risk curve in black, which indicates that the GraphCast is better at the task, although age-risk is still better at 12-hour predictions. This is not totally surprising, as this is consistent with the RMSE for surface temperature. However, it is still great to see that the gains in RMSE extend to extreme predictions. And in the paper supplementary material, we show results for other variables relevant to extreme heat, as well as other metric regions, and including extreme cold, of course. And in general, we found that all these extreme phenomena tended to align pretty well with the RMSE results. So going back to your question, a fair comparison against age-risk. One problem that we found is to decide against ground truth when computing metrics for age of the models. And to understand why, let's go through what happens when we make a forecast with our model. So we take an initial state from era 5 reanalysis, which is this 40 years data set, and we feed it to GraphCast. And we do this because era 5 is the largest data set across all the years that we use for training. And so we, of course, want the biggest model for optimal performance. And this is going to produce a trajectory forecast. And then we compare it against the era 5 reanalysis dataset to compute all the metrics result. So far, so good. However, we also want to evaluate age-risk, but we don't have access to the age-risk model. So what we do is we use forecasts that have been historically saved for each year from a specific initialization, and we call this operational analysis. And the problem is that the operational analysis and the era 5 reanalysis, they're very similar, but they are actually not the same. And this is subtle, but as a result, if you compare age-risk forecast against the era 5 reanalysis ground truth, you will find higher errors than expected. So after careful checks, we essentially decided to compare against kind of this operational analysis itself. It makes essentially age-risk look better than if we were to compare it in terms of era 5. There's also another issue, which is this assimilation window that we were talking about on your question. Essentially, the intuition is that era 5 reanalysis goes from 9 to 6. So you can see that for some horizons, some starting points, so what an assimilation window is that we integrate all this raw sensing information within one window to inform the weather states at 0 hours and 6 hours. And so the 0 hour starting point actually has some information leakage from 9 hours into the future. So if you're not careful, the models initialized with era 5 actually have a 6 hour advantage compared to the operational analysis, which have different assimilation windows. Operational analysis always has 6 hours assimilation windows and always kind of 3 hours, looking 3 hours into the future. And that's why we decided to only show results that started at 6 hours, because 6 hours only has 3 hours into the future. And similarly, we also only show results usually going 12 hours into the future, so multiples of 12, because then you're in the same point in the assimilation window. So we only use 6 hours and 18 hours.
So, okay, so you still have this leakage, but it's the same as...
Exactly. Now we have leakage, but like age-risk less and like any weather model used in the real world, they all have 3 hour leakage. And that's why they start from 3 hours in a deployment scenario, they start from 3 hours into the past. So we have to be very careful. In some papers initially, and even us initially, we had made this mistake of comparing results on age-risk at 0 hours and 12 hours, which is kind of the most intuitive. But we found that actually we had the 6 hours leakage bigger than age-risk. And so I think we had actually this mistake in the first version of the paper, but the second version of the paper corrected this. Or maybe, I forgot, maybe we corrected it even before the first version.
Got it.
Yeah.
I'm just curious. So when they, let's say the operational analysis, if you take data 3 hours into the future and absorb it, assimilate it, then you start rolling forward again, you're going to repredict essentially kind of what you trained on or what you conditioned on. And then, of course, you're going to make novel predictions. What's the discrepancy like when you repredict back what you've already seen? That's like sort of internal validity, right? Do people track that?
Yeah. That's a great question. We actually found this this issue, and we found that it's actually much easier to predict within a simulation window than across the simulation window. As far as we know, when we were discussing with the weather agency and other models, we were the first ones to kind of see this being a big issue. I think people had kind of, because the ERA5 reanalysis dataset had not been used as a machine learning dataset until last year, there were some of these issues literally had not been realized, and so yeah, people were reporting it as if it was the same as simulation window. But we do see that the model is essentially learning two models. One within the simulation window, and it does very well. That doesn't have zero error. We think for two reasons. One, it's not learning true age risk, not learning the true physics models, and two, the physics model also does not fully predict itself within the simulation window, because it had to explain all this noisy sensing, right? And then once you cross the simulation window, you have very high errors. Well, not very high, but like comparatively very high errors. Yeah.
Yeah. Thanks.
So what would be the optimal way of doing this? 'Cause, I mean, the setting you have is the raw data is not dense enough for you to train a good model. So you use this reanalysis of some sort. Would the right, most favorable approach would be to have a different assimilation policy and rerun the entire ERA5? Would it be, would you want to have, I'm not sure, do you have ensembling for ERA5? Would that help or hurt you?
Yeah, that's a good question. So I think there is two answers to this. One is, in the short term, the best thing to do is take ERA5, or at least what we've started doing is we take ERA5, we fine tune on this is a smaller operational analysis data set, and then we are comparing apples to apples, and everyone's happy. And that's actually, we've already deployed. So if one goes to this European Weather Agency, we can already see the GraphCast models running on real fit at real time, and that's how we actually did it. We trained with these 4 years on the ERA5 and then fine-tuned. However, there is an even better thing to do, which is kind of probably long term, which is just training on raw observations, right? Machine learning doesn't care about the type of data that it runs, so we should just go to the rawest, richest source of information, which is just taking raw observations, which they will not be uniform in time or space. So it's actually a very challenging research problem to work with this, and also probably they're huge, but it's probably what you want to do eventually, which the model then will have to learn to assimilate the data itself as well. But that's kind of more long term. Cool. So in summary, using this 6 a.m. and 6 p.m. Was solving two problems. First, there are 5 initializations at midnight and noon could potentially have a 9-hour look ahead from a simulation, and this can could have given an advantage to GraphCast. So we only used 6 a.m. and 6 p.m. So one issue though, and that's why you had this kind of dashed line, is that age risk only, the published age risk predictions only looked up to 3 days, 3.5 days, sorry. So after this 3.5 day curve, we actually had to compare the 6 a.m., 6 p.m. GraphCast against 12 a.m. and 12 p.m. performance of age risk. Of course, not predictions, but literally the RMSE metrics of 12 a.m., 12 p.m. against 6 a.m., 6 p.m. And so the second is kind of going back to Kevin's point about it's easier to predict within the same simulation window rather than across the simulation window. So what we do is actually only report errors every 12 hours so that we're in the same point in the simulation window. And we found this to be the most consistent. Another disadvantage of the RMSE metrics is that in general, RMSE rewards models that average over uncertainty. And in fact, models like GraphCast are often trained to minimize RMSE, which means that the training itself may teach the model to blur. And in fact, if we look at the power spectra of some of the variables, we see that indeed, as we increase the forecast lead time, some of the power in the high frequency diminishes. So of course, the question is whether it is possible that GraphCast metrics are better simply because it blurs more when the age risk, which is just trying to mimic the raw physics, does not blur. And so to control for this, we recomputed the main metrics, but we now applied a post-processing step, which adds a spatial filter to each of the models allowing it to blur the output. And the filter is specialized for each model, each variable, and each lead time, so that each filter allows to minimize our MSE. And this is what we call in the paper optimal filtering. The plot on the right shows a dotted line, how the results of each model change as you apply this optimal filtering. And interestingly, not just HRIS, but actually also GraphCast can obtain a lower RMSE by applying this optimal filtering. But we fortunately see that GraphCast still outperforms HRIS after this optimal filtering. So we must be learning a better weather model, not just kind of tricking this RMSE metric. Cool. Yep.
Sorry, I didn't understand that. So you're essentially sharpening the generation from GraphCast to make it, you're unblurring it with a post-processor?
No, the opposite. We are blurring it so because we know that blurring cheats the RMSE metric, we allow both GraphCast and HRIS to blur.
I see. So HRIS has a free parameter for each variable to blur as much as it wants to minimize its error.
Exactly. And we thought that that was the main thing, right? We wanted to allow HRIS to trick the RMSE metric, because we thought GraphCast probably was tricking the RMSE metric by blurring. So we thought, let's give HRIS that option as well.
I see. Okay.
And then we also added this to GraphCast just in case. We see that it helps, not as much, right? You can see that the black line goes lower much more than the blue line goes. And in particular, one thing, let me see if it can be seen in these graphs. Yes. You can see that the dashed line is only better than the blue line, like the dashed blue line is only better than the non-dashed line after about 3 days, which is our training objective. We only train up to 3 days. And we hope that after training up to 3 days lead time, it generalizes up to 10-day performance. And as you can see, that blurring doesn't help much with less than 3 days. And we think that's because indeed the model has learned to blur up to 3 days. And then after this, optimal filtering actually helps to blur even more and fully kind of cheating as much as possible this RMSE metric by blurring. But we see that when you allow both models to blur as much as they want, GraphCast still does better predictions.
Mm-hmm.
Yeah, thanks for the question. Okay, so I guess that the takeaway is that the fair comparison between operational models and ML models trained on AI5 is pretty tricky, especially when models are initialized from different analyses and when models have different or of different nature, right? So one potential solution, which I believe it is becoming more common recently, as we were discussing before, is to evaluate the model on the operational setting rather than AI5. So in terms of potential solutions, I guess this is one of them. And so this is the results on the operational analysis themselves after we fine-tuned. So after the first archive, we published this. And so one suggestion is that hopefully a next version of AI5 will have these aligned assimilation windows that are closer to the operational setting. And as I was saying before, to Greg's question, really the best thing to do is evaluate against observations. So just one thing that I wanted to show is that we wanted to check the biases of our model in certain regions of the world. For instance, this animation shows where the model underestimates, which you can see in blue, or overestimates in red, the surface temperature, and it does so in different places on the Earth. And as the animation goes along, it's different forecast lead times. So looking at this plot, we see that indeed the model has biases, and that these biases change with forecast lead time. However, while this may seem like a lot of biases, actually these biases are comparable to the biases that of HRIS in terms of magnitude, and they are both of them grow in time. And we also actually found some correlations between HRIS and GraphCast in terms of the biases. Cool. Another thing that we did was training to make sure that, like, to understand really the effect of the data recency on the model. And what we did was evaluating on 2021. And we tried training on up to 2018, which is our main model. So instead of, we trained up to 2017, and the main result is testing on 2018. But now we looked at 2021. And you can see that performance is still better than HRIS, but not as much as one would hope. But as we add more recent data, performance keeps improving and improving. And so the closer we go to 2021, the better we do on 2021, which is nice to see. But we also indicate that there's probably some distribution shift. We don't know whether this is due to climate change or also better sensing modalities, right? Because the ADA 500 simulation data set has been created with raw sensors, and these sensing modalities have been improving over time. Another ablation that we did in our model is removing these long edges that we were saying before. Maybe they were learning some non-physical parameters, and we see that in general they tend to help, especially on geopotential and mean sea level pressure, which are essentially the same quantity at different levels of the atmosphere. And these tend to be smoother fields, so we think that probably that's why having these long edge dependencies helps in both cases, but it seems to help across the board. And finally, we also looked at the effect of autoregressive training, right? So we have the option of just training to do well at 6 hours, or training the same model to do well at 6 hours and 12 hours, or training it up to 12 hours, autoregressive step. And we see that it's essentially performing a trade-off. So the model, when we only train it at one autoregressive step, is the best model at one autoregressive step. And as we increase the number of training steps, we're essentially shifting the curve and balancing, doing better at longer lead times with doing worse at shorter lead times. So in conclusion, the GraphCast outperforms interest, which is the best operational model. In many ways, we have seen how it does better in the typical RMSE metrics, but we have seen that also this translates to better real applications. It's also worth noting that now inference just went down from 1 hour to 1 minute, which also allows us, if we wanted to in the future run and predict an ensemble of predictions, not just a single prediction, that would also be much cheaper to do. And we think that we have to be careful and make comparisons that not just apply to RMSE, but real applications that benefit the end user. And the second conclusion is that deep learning weather models are probably here to stay. So last year and 2023 have been kind of key years where deep learning has started to surpass numerical weather prediction. And as the data keeps increasing, any Earth scale modeling using deep learning is going to outperform classic physics. And that's it. Thank you for your attention.
Yeah. Well, thank you very much. Are there questions in the call? Well, okay. So let me. Oh yeah, you, Jung?
I have a question about have you aware about Google has already released our weather bench, and what's the difference between the weather bench and this? And I see weather bench has also include this paper for GraphCast and also the Pangoose transformer weather model. And then so what will be that you guys, because I know Google has been consolidated with DeepMind, so do you guys will like actually cooperate together or just different types of model? And what's the purpose have two different types of model? So there are so many weather forecasts, and also NVIDIA has their weather forecast too. And I just want to know the purpose, because I'm a hydrology purpose, and there are so many, and I'm not sure that weather forecast will helpful for hydrologists. Yeah.
I didn't understand the last sentence, but in general, so there's two answers to your question. One is what is weather bench and its relationship to GraphCast. Weather bench, as kind of the name implies, it's more like the benchmark than the methodology. So weather bench, I forgot if actually there is some sharing between the authors in our paper and weather bench actually. I was not involved in weather bench, but many of my colleagues were. And essentially just think about it as the benchmark. So just as a standard platform to evaluate weather models. And yeah, thanks for sharing the link. And weather bench 2 was, which is the link you shared, was recently open sourced to essentially just standardize weather prediction, because there are many things that one can do. There's many mistakes that one can do when evaluating weather models, and they make the right decisions, hopefully, and to make a standard for the industry. And actually, the creation of that benchmark itself kind of answers I think the second part of your question, which is why that many models, and is it worth it to have that many models? And my answer is that probably yes. In research, kind of this healthy competition across many different ideas, different teams, that's what makes progress go farther, and we build on each other's ideas, and we create but some amount of independence to be able to explore different paths. Like for instance, NVIDIA uses Fourier neural operators. Pango was using transformers. We use graphical networks. each of us is going to discover different things, and so we're going to build on each other's discoveries. And I think that's kind of the beauty of research, and kind of also, yeah, what enriches this field.
Yeah. I'm just follow out your answer. So I want to know, like, do you just give you a case, like, because you mentioned about atmosphere river. So in case all this model like predict, so how does your model predict for atmosphere river landfalling location or landfalling? I mean, the IVT path will be much more accurate than actually using the weather satellite measurement. I'm just curious. Yeah.
I'm not an expert in this. I think Remy Lam, if you want to send him a message, that he was actually the one that did the atmospheric rivers experiment. But as far as I remember, the atmospheric rivers is literally a formula involving a few of the variables for a few grids. So we have a few grid points in our evaluation, and we literally apply that formula both to the true weather as well as our predictions, as well as Idris's predictions. And we literally compare those numbers, which one is closer to it. I don't think we have paths in the atmosphere or anything like this. It's not like cyclone tracking. I believe it's literally predicting a specific quantity, which I forgot exactly what it was. I think it's what we call IVT, if I remember correct. But again,
that's right. Yeah. That's how I did in my PhD.
Yeah.
Thank you.
One thing, I guess this is a good show of the fact that the machine learning community, we know very little about weather. We try to learn as much weather as possible, and kind of we think that we try to be as careful as possible and as responsible as possible in our evaluation. But we've also been in talks with weather experts to make sure that our predictions are consistent and meaningful as possible. And so, yeah, any input that you have, in particular in this field, if it's your expertise, if you message Remy, I'm sure he'll be very glad to talk to you.
Thank you. Okay.
One more thing, I'll just leave you a link to Freddie Cantor, who I just realized is at Google now, who does hydrology. So he's done LSTMs for hydrology, and as far as I understand, like hooking up different river systems. And he's done pretty well compared to, physics-inspired hydrological models. So that's another interesting approach.
Sure. Thank you.
And Raj?
Yeah. Oh, hi, Ferran, this was great. I think my question is more as a weather enthusiast or like a hobbyist. If I want to do a crawl, walk, run on your model, do you have some tips or some like pointers that we can use just to have it more on trying to stand that up, just to do it like your my own like local model for where I live? And also I was just wondering if you had some tips or some pointer or some like document you can point me to like stand that up from that standpoint.
Yeah, I would recommend we kind of the two links that are on the slide. In particular, we have all the code for available on GitHub. I don't think we have code for training, but again, if you're saying more like an enthusiast perspective, training is super expensive, but literally running the evaluation, like running the model prediction is relatively cheap, can be done with a regular GPU. Or also starting with a with a smaller model. I think we also open sourced a smaller model that runs at lower resolution. That would also be a good example. And then another thing, I forgot if he has already published the paper, but there was a recent large-scale deep learning Bonn conference where there was a PhD student that used ideas from GraphCast to run a local model, and also.
Very cool. Awesome.
And both ideas from GraphCast and GraphCast predictions, I believe. So to combine it with a higher resolution model that was local. And the intuition is that our resolution is still not the resolution that one would get on your phone. So if you get your predictions on your phone, you're using a higher resolution model. But how it works in practice is that it's informed by a lower resolution global model like ours.
Oh, awesome. That is great. Awesome. Thank you so much. Appreciate it.
And performance-wise, so that's probably a big deal in terms of how do you fairly compare the performance? Because you're already based on error, so that's been already done. But the alternative models, how long do they typically take, and like for a given prediction?
Yeah, if I remember correctly, I think it's on the order of 1 hour. It's definitely much more than 1 minute, which is roughly what our predictions take, and that's kind of one of the big advantages that ML brings to the table. And that's actually, if you look at some of the papers from 1 year, 2 years ago, that's how they were justifying. They were worse than traditional weather models, but they were much faster. Now we have both faster and better. So that's very good.
And in terms of training, how long does that take?
No, in terms of training, it's expensive. So we have about 3 weeks, 3 weeks and 3 days, I guess. So 24 days. But it's hopefully amortized. Yeah. So one thing that's interesting about weather models is that the training cost is bigger than the test cost, which is not often the case for many ML models.
Do you have any notions? So you said 32 GPUs, and versus 10K CPUs. Is there a scale comparison between those two?
I think it's probably cheaper in our front. I'm pretty sure it's cheaper in our front. And actually, but one interesting thing is that these weather agencies now have to shift some of their compute to GPUs because their clusters have been CPU based. But I think the compute cost is much lower now, which is good for the field.
Got it. Yeah, Kevin?
Yeah, you mentioned ensembles earlier. Like, since you're already hooked into ECMWF, they have an ensemble forecast. Could they not just take the initial conditions and run your GraphCast code 60 times and, you'd fill an hour, right? That seems conceptually straightforward. Is it just an engineering task, or is there open problems there?
No, we've done that internally, and yeah, it's good. It gives good results. We haven't published this yet, but it can be done because we've done it. Sorry, I forgot. Sorry, let me just make sure I answer you properly. Sorry, we haven't hooked up, but we've done essentially something very similar of essentially perturbing the initial conditions and evaluating this, and it actually worked great. So just to complete the answer, we say that we're better than the best deterministic model, which is what the ECMWF calls iterative. But as you were alluding to, you can perturb initial conditions, run it 50 times, average the results. That gives better performance than the model we compared against. This is called ENS. But of course, we can do the same to our model, perturb it and average it, and that gives even better performance. And we think that this is probably better than ENS. We have to make sure that internally we think that it's better, but I don't want to make this big claim yet because we have not published the result.
So actually, this is interesting. So typically, what they do in weather, folks, they have an ensemble common filter, have these 60 models running. Some of them are wrong, kill them, kind of push some of the existing population to take up the variance of the weather and so on. Is that your approach, like ensemble common filter kind of thing? Or the neural nets give you a different way of getting those distributions?
Oh, yeah. In our case, there are literally 50 separate predictions if we wanted to make them. There's a different question on the data simulation, right? So if you wanted to say what's the weather state, you would need some form of filtering to eventually come up to the present, an estimate of the present state. We are relying, as I was saying, kind of at the very beginning of the slide, it's not a pure end-to-end ML approach because the assimilation, the initial state, the input state from which we start is still NWP based. So I want to be very clear about this. We're not a pure ML approach. And so they are probably running some of the filtering that you're talking about. But we don't. On our front, it's literally, this would be like 50 neural network evaluations.
No, but then the Kevin thing was describing is you have 50 of these things. You take weather samples, and now, in typical weather prediction, you kill some of those which are completely wrong, and you make clones out of the remaining population. That's the common filter. But I get the hope that if you have like a variational neural net or something like this, you don't have to do something as, I don't want to say as simplistic as an ensemble common filter. You might get some of the Bayesian priors into that process.
I see. I'm sorry, I was more familiar with the kind of filtering used for kind of assimilation than for the future prediction. So I misanswered your question. So what I can say is that our preliminary experiments that I was talking about to answer Kevin's point about the perturbed ensembles were literally 50 independent samples.
Right.
We are working, and I think some other teams are working in probabilistic methods that predict the distribution and to do this more properly, but we still don't have concrete results to show.
Yeah, fair. Well, yeah, thank you very much. It was fantastic. Thanks.
Thank you.
Thanks.
Have a great day. Bye.
Bye.